Good morning. This is the report of the second lab practice that it's called Reduction of Oil's Viscosity. We are the group 3 formed by Nicolas Pedraza, Juan Camilo Ordoñez, and Paola Medina. First of all, we are going to explain two main concepts and definitions. The first of them is viscosity, that is a term of physical property of fluids due to the forces of molecular cohesion that result from the fluid's opposition to movement. And the second one is heavy oil, that is high viscosity oil that can be transported through oil pipelines. First of all, we are going to explain what is visbreaking. It is a chemical method used for reducing viscosity of heavy oil. It proposed to add chemical additives to it, which help to reduce its viscosity. And in this case, we use acetone and toluene. As imagined, it is commonly used in petroleum industry due to the challenge of the high viscosity that the petroleum nowadays has, and also because it exists a huge demand for petroleum energy, and now we have to use another alternatives for reduce the viscosity of heavy oil and extra heavy oil. And it is important because it doesn't have the disadvantages commonly seen in other methods, such as thermal methods. Like the disadvantages that it commonly has are that it the equipment has a high cost and also a huge fuel consumption. And well, this method doesn't have that disadvantages, and also it helps to reduce the viscosity of oil. For understand better how this happens, we need to know the components of oil. It is composed mainly by four things. There are saturates, aromatics, resins, and asphaltenes, also called SARA. These last ones are the key component in the high viscosity that oli has, because they form aggregation and clusters through polar groups and alkyl chains. That's why, for reducing viscosity, we need to destroy the aggregation between asphaltenes. And the way for evaluating this is through molecular dynamics. That's why the objective of this practice is to analyze the effect of organic solvents on the reduction of crude oil viscosity.
Now let's talk about the methodology that we divide in three steps. The first step is before the rheometer. Firstly, we select a solvent that in our case was toluene. The second step, in the extraction cabin we pour 30 milliliters of oil and 5, 50 or 20% of the volume of the oil in a beaker depending on the group. In our case was 5%. And finally, in the extraction cabin, we mix the solvent and the oil until we get an homogeneous mixture. The second step is the rheometer. In order to use this equipment, firstly, we need to calibrate it. And it has like a few steps. Firstly, we need to open the airflow, extract the secure, then turn on the chiller, and finally we can turn on the rheometer. In order to use the rheometer correctly, we need to calibrate the rheometer without plates firstly, and then we need to select a geometry, that in this case was a coaxial cylinder, and then we need to recalibrate it. When we done all the calibration, we pour 25 milliliters of the solution in the rheometer glass, and then we locate the geometry 5 millimeters under the top limit in order to create a gap. Then we need to select the method, that in this case was steady state flow with a sharing limit between 1 and 100 with 5 steps and with a temperature of with 20 Celsius. And finally, we drop the plate and press play in the PC in order to start the rheometer. The final step is after the rheometer. Basically, when the rheometer finishes collecting the data, we need to obtain the data and finally clean the beaker and the rheometer glass with barsol in order to eliminate any waste of oil left.
Okay, now we're going to talk about the results and the analysis related to them. First, we have the data from the crude oil sample. In this table, we present the rheology properties from the crude oil sample. All these data were collected from the rheometer in the lab. First, we have the shear rate, then the shear stress, and finally the viscosity. That are the properties that we're going to analyze. But we also present time, temperature that shows us that the test was isothermal, and finally the normal stress. Okay, now we're going to present the results in a graphic way. We have some important plots that we obtained from the software MATLAB. First, we have shear stress versus shear rate, and then viscosity versus shear rate. From these two plots, we can say that the crude oil behaves in a Newtonian way. That's first because of their linear relation between shear stress and shear rate, and also because of the viscosity that remains virtually constant through the test and it doesn't change with the applied force. And we can see that the viscosity of the crude oil is around 11 pascals times seconds. Now we can also know that the relation among these three properties is shear stress equals viscosity times shear rate. So the viscosity is going to be the slope of the graphic between shear stress versus shear rate. These are some plots that we obtained from the third chapter of the Chemical Engineering Fluid Mechanics book, and these show the different behaviors of different fluids in these kind of tests. First, we have the shear stress versus shear rate, and then the viscosity versus shear rate. And we can say from this that the crude oil is indeed a Newtonian fluid because of the behavior in these two plots. Now we're going to present to you the results from the sample with 5% of acetone as the diluent of the crude oil. This is the same table that we presented with the crude oil sample, and we already know that the main properties are shear rate, shear stress, and viscosity. From now on, we can tell that the viscosity is smaller than the viscosity of the crude oil. But we can see this better comparing these two plots with the ones that we already presented for the crude oil. First, we have the shear stress versus shear rate, and this shows us that the linear relation between shear stress and shear rate is still there, but we can tell that the slope is maybe a little bit smaller. Then we have viscosity versus shear rate that shows us that the viscosity is now around 4 pascals times second. So the acetone as diluent has actually a great viscobreaking character because now the fluid has almost half of the viscosity that had with the crude oil. And also we can see from this graphic that the viscosity remains constant throughout the test. So even though now the fluid has 5% of acetone, it still behaves in a Newtonian way. Since we already analyzed the data from the crude oil sample and the one with 5% of acetone, that was the one given to our group, we can now discuss about the results from the work of other groups with different configurations of solvents and see the viscobreaking properties of these solvents as a whole. Just like we did before, we present to you now the graphics for shear stress versus shear rate and viscosity versus shear rate for all the different configurations of solvents that were used in the practice for the different groups. We used acetone and toluene as solvents, and in three different configurations, 5% of the solvent, 10%, and 15%. So we got finally 7 treatments, including the crude oil sample. From the first graphic, shear stress versus shear rate, we can conclude and finally see, just like we were analyzing before, that the slope of the function decreases as the viscosity of the fluid decreases too. From the second graphic, viscosity versus shear rate, we can see that the viscosity remains constant in all the configurations, so the behavior is still Newtonian. And as the percentage of solvent increases, the difference between the reduction in viscosity is fewer. From the two graphics, we can finally conclude that the best configuration was toluene at 15% because it reduced the viscosity of the oil almost at zero, and that's something that we're going to look for in the oil industry because it is closer to the viscosity of water, that is 1 centipoise or 0.00 pascals times second. In order to see the final results in viscosity of the oil, depending on the different configurations in the solvent, we are going to present to you a table with the mean viscosity of the data from the rheometer. From this data, it is easier to conclude that the best solvent was toluene in terms of viscobreaking properties, and as the percentage of toluene increased, the viscosity of the fluid decreased. But in general, the two solvents were good at the viscobreaking properties because the least configuration, that is acetone at 5%, was enough to decrease the viscosity of the fluid more than a half. And also we can see in this table the standard deviation that demonstrate once again that the behavior of the fluid is Newtonian because it is mostly constant. From the research that we did, we could conclude that the selection in the solvent in the oil industry depends specifically in the quality of the solvent, that is the polarity, and it is better when the solvent is more polar. The size of the molecule of the solvent, that is better when it is smaller, and the solubility of the solvent in the oil, and it is better where it is more soluble. And also it depends on the cost of the solvent and also its availability. We could conclude from the solvents in the practice that the best was toluene, but it is also the best one in the general oil industry, and we can see it here in the graphic for viscosity versus percentage of solvent. And the toluene is the one that reduces the viscosity of the oil the most.
As a conclusion, we can say that depending on the type of molecule that is the organic solvent, it affects the viscosity. Polar solvents, that in this case was toluene, are better, decreasing the viscosity of the oil against hydrogen molecules that have hydrogen bonds, like acetone. Also, we can conclude that industry should take in mind the type of solvents they use, because if we compare, in this case, toluene against acetones, we say that acetone is cheaper, but toluene is better. So it's very important to see different solvers in order to make a good decision. And finally, it's not just the solvent affects the viscosity. This is another conclusion. Industries should take this in mind, and also it could be very interesting to analyze the viscosity of the oil in different pipelines like fiberglass or sulfuric acid pipelines that are in this case corrosions. Finally, these are our references. Thank you so much and have a good day.